Hello, hello. This is Statistics Special Topics Talk number 19. There's a Bayesian method for that. I'm Mark Williamson for the TRANSCEND project, Translational Science Engaging North Dakota, the successor to Dakota. And I'm at the University of North Dakota. And I'm very excited to give you this talk today. The goal of this module is to show how the Bayesian utility belt can tackle any statistical test. We'll cover t-tests galore, ANOVA of all flavors, correlation and regression on demand, frequency analysis for good measure, and advanced models for winners. Hiya kacha! Let's get started with Bayes. Setting up the intellectual avenue here, let's talk a little bit about Bayesian thinking. So Bayesian analysis comes from Bayes' theorem. Bayes' theorem sort of simply states that the conditional probability of an event is based on prior knowledge and new evidence. You can see an equation here, which is essentially the probability of A given B equals the probability of B given A times the probability of A all over the probability of B. So essentially, Bayesian thinking is really taking what you already know about the probability of something, getting new information, getting data, combining the two to get a sort of posterior updated information. It's all about sort of updating how much you know about the probability about some sort of outcome. So a lot of times this is sort of visualized by thinking posteriors, or sorry, distributions. So you will have like a prior distribution of like, say, maybe where you think the mean of a population is, some sort of distribution that kind of tells you how confident you are with your estimate of what that maybe say mean is. You actually take data or likelihood, so you collect data, and then between those two you get a posterior of like this new update of like where that mean is or whatever thing you're measuring. Now something linked to Bayes' theorem is what's called Bayes factor. Now if you think about frequentist analysis, what typically happens is you run some sort of statistical test, you have a test statistic, and then you have a p-value associated with that test statistic that tell you sort of how likely that is to get that or stronger of a test statistics. So Bayes does not have p-values, but it has something analogous, which is a Bayes factor, which is the ratio of the likelihood of one particular hypothesis to the likelihood of another. Typically, this comes in the form of the ratio of the alternative to null. And so you can have a table of different Bayes factors and to help give you interpretations. Now, it's not quite like p-values, but again, it's sort of measuring how confident or how much evidence there are for whatever hypothesis you're testing. Now, because this is a ratio at 1, essentially the likelihood of the alternative is the same as the null. There's no evidence. So 1 means no evidence. Now, if it's positive values, that means there's evidence for the alternative. And as you go higher, it becomes stronger and stronger, anywhere from anecdotal to extreme evidence. Now, if the null is stronger, it'll be a fraction. So again, low fraction is anecdotal evidence of the null, all the way to a very small fraction is the extreme evidence for null hypothesis. So if you're really just getting started with Bayes, doing something like a Bayes factor helps get your sort of feet wet on running these sort of analysis and interpreting the results in a way maybe you're more familiar with say p-values. Now, when it comes to actually running Bayesian analysis in something like R, which I'll be using today, R, I would say there's a couple of what I call authoritative approaches. If you're going to like do nothing but Bayesian analysis, you want to do it sort of the most high octane. These would be a couple approaches. There's sort of like the STAN methodology, so you could use the package R-STAN-ARM. Really a four-step practice to make Bayesian estimation routine. For common regression models, you got a posterior distribution. You draw from that distribution using MCMC, Markov chain Monte Carlo. You criticize that model and you analyze manipulations of the predictor to see a best fit model. Another authoritative approach are called the JAGS methodology. So RJAGS is a package, or more properly, an interface from R to the JAGS library for Bayesian data analysis. However, today we're not using that approach. We're using my approach, our approach, where we're going to start with the frequentist model. So analyze the data what you would if you're just doing things with p-values, frequentist, whatever. And then compared to, I'd say, the quickest and easiest, the most sort of analogous Bayesian setup, just to be able to start comparing, like, how do these things differ. So that's our approach today. So let's start with t-test. We'll cover one sample t-test, two sample t-test, and paired t-test. With the one sample t-test, we'll use the sleep data set. So this is data which shows the effect of two sulfuric drugs. And so an increase in hours of sleep compared to control on 10 patients. So we'll sort of combine both drugs to say, does taking any of these sleep drugs improve sleep compared to compared to the control. Anyways, the traditional approach would say something like using using the function t-test, and we're going to save that as an object. We're going to have this a two-sided test. We're going to use, because this is a one sample t-test, we want to compare whatever all the sleep values to a single control, like a single constant. So we're going to take that as 0. That's going to be a mu is 0. And we're going to say paired false. Some of these things are default. You could simplify this up, but if you want to kind of specify all these things. Anyways, so we'll get that, and we can call it and see if that is significantly different. Now the Bayesian approach, there is this Bayes factor package in R, which is really helpful and has a lot of ways to get Bayes factors and things out that is very close to how the format of the standard test is made. So we can create a variable called b t-test1, and we're going to use this function t-test bf, so Bayes factor, which do x is sleep extra, our constant is mu. We pull that out, and then because we're doing Bayes factor, we can essentially get chains. We can run the function posterior for iterations, and we essentially can sample from the posterior using MCMC. And we can get summaries of these chains to sort of get the sort of posterior distribution, and we can plot some of that stuff. So there's a lot going on there, but it'll help when we visualize it. Now, to sort of orientate ourselves, this is a box plot of the data here. All the points here is the different observations, the different people, and the amount of extra sleep in hours. You can see here that the red line is 0, so that means there's no 0 sleep. You see that most of them are above the red line. So it looks like there might be some evidence that taking one of these drugs improves the amount of sleep. So let's actually test that formally. So the results of the traditional test, one sample t-test, we see here that we get a t-value, and based on that t-value, the p-value is 0.0029. So that is less than 0.05, so we call this significant. In fact, we can get the mean. We see 1.54, which means on average, participants had 1.5 hours of extra sleep taking these drugs compared to a control of nothing. So, okay, that was significant. What does Bayes do? Well, Bayes factor analysis, it'll spit out the number here at the end here is going to be our Bayes factor. So it looks a little different, and now because we're doing a ratio, this is 14.5, so 14. So that's positive, so that means there's evidence for the alternative. And 14 falls within the range of strong evidence for the alternative hypothesis. So both things are saying the same thing. However, if you kind of run those chains, you can get a posterior sort of density, sort of an estimation of the mean in Bayes, and we can see here, I kind of just put just that part mu. That's the mean of the sleep. We can see here that it looks like the peak is around 1.5, like we would expect, and it spreads out here, and you see it really looks like, yeah, it is greater than 0. That there's not a lot in that distribution at 0. There's a little bit of some tail here, but that kind of gives us fairly high sort of confidence that that this really is greater than 0. All right, 2-sample t-test. We'll use chick weights. This data set's an experiment to measure the effectiveness of various feed supplements on the growth rate of chickens. Now, I have restricted this specifically to 2 groups, otherwise it would be ANOVA. So we'll just look at 2 groups. Is one treatment compared to another treatment, does that change the growth rate of chickens? So a traditional approach, very similar to what we see before, we'll use t-test. So we're going to actually use sort of the function setup is so weight as a function of feed, and feed right now only has 2 groups. And we're going to use the variance equals true assumption. If we're doing the Bayesian approach, very similar. We can use, again, specify the formulas setup, so weight as a function of feed, similar outcome, and then we're going to do these what I'm called chains, where you sample from the posterior of this test for 10,000 iterations, and we can pull out information, especially on plotting the outcomes of these posterior samplings. All right, so just again an orientation graph, box plots. We see here the 2 feed types are horse bean and linseed. It really looks like linseed has results in higher weight of chicks, but that's what our test is for. So with the 2-sample t-test, we get a p-value of less than 0.05, so that's significance. We can see here, indeed, looking at the means, the mean of the linseed group is over 200. The horse bean is about 160. So it's a significant difference. Now, if we do Bayes, we get a Bayes factor of 5.9, about 6, which is moderate evidence for the alternative hypothesis. And we can plot things here, and this is, so what this actually isn't the means, but I think more or less the difference in the means. So from here, it looks like the difference in the means is about 80. So it is a little, this one looks like it's a little more like 50. So maybe there seems to just be less certainty about that, but it really does look like, you notice how it's not that, the peak is not that close to 0, but a little bit more of the tail isn't 0 than our previous example here, which sort of lends the fact that we only had moderate evidence rather than strong evidence. So maybe a note here, plotting some of these outcomes of the posterior sampling for Bayes factor can sort of be tricky. The names aren't always clear. There's often a lot of graphs. I'm usually just printed off the 1 or 2 that are relevant. So you really have to be able to kind of work your way through and play around with it to make sure you're understanding what is actually being spit out at you. And that's certainly something I'm trying to get better at as well. All right, we'll finish up with a paired t-test. We'll again go back to our sleep data. Now, I sort of modified it because now I want to compare between a paired test, is where something like one individual takes a drug and another drug, which is in the case here. So there's pair. The tests aren't independent. So because in our 1-sample t-test, we just pull everything together. And this one we're going to specifically split out, call it paired true, and we're going to compare X and Y. It's going to be sleep group 1 versus sleep group 2 because there was I think 10 individuals that each took both drugs, on alternative nights. So we want to capture that in our data here. And we can do the same thing for Bayes. And now something I did with the traditional approach here, I can split them out by group like this. I also did something where I created a variable called sleep diff, where I just subtracted the mean, or the sleep measurements from group 1 from the other, and then just actually did pair false and compared it to 0, because it really turns out with paired t-tests, they're essentially functionally they are equivalent to a 1-sample t-test where you're measuring the difference between the paired values compared to a constant. So I just did it two different ways, which would give us the exact same results. And then for Bayesian, I just used the sleep diff variable to make things simpler. Again, sample from the posterior, plotted, etc. And so to kind of show us what we're going on here, I did a spaghetti plot. We can see here that there's the two different groups, and then the lines are the individuals. So it really does look like, so we have the lines all mostly, I think almost totally all go up, which seems to indicate that group true had higher sleep for all individuals, and so probably collectively. I think there's maybe like one individual that maybe went down slightly. Anyways, so let's run this test here. And if we do it the paired t-test way, this is significant. The mean difference was negative 1.58. So I think that, yeah, because it was comparing 2 and 1. So on average, the group 1 had about an hour and a half less. So the drug 1 had an hour and a half less sleep than drug 2. And if we do one sample t-test using the sleep diff, exact same outcome, because really you're doing the same thing. Now if we use Bayes, we get a Bayes factor of 17, so strong evidence for alternative hypothesis. And again, this is getting the mean diff, the mean of the sleep diff, and this is now, yeah, about 1.5, 1.6. So tracking nicely. All right, with that, let's switch to ANOVA. Again, ANOVA is sort of like the logical extension of a t-test for more than two groups. So if you say, think of a chick weights, it was like, there's two different groups like linseed and what, cowbean or something, but then the full data set had 3, 4, 5 different groups. So you use something like ANOVA. We'll look at one-way ANOVA, in which there's just one, variable, one group. Two-way ANOVA, we can look at multiple categorical variables. You can do 3 or 4-way, but we're just going to stick with 1 and 2. They just extend from there. And then repeated measures ANOVAs are sort of like the paired t-test extended, where individuals will be repeated across time or treatment or whatnot. So with one-way ANOVA, we'll be using the dataset tooth growth. This is response to the length of odontoblasts, so cells responsible for tooth growth in guinea pigs. Each animal received one of 3 dose levels of vitamin C by one of 2 delivery methods, orange juice or ascorbic acid. So for one-way ANOVA, we'll just use a single variable. We're going to be using dose. So there's 3 levels there. So we can use the function AOV, and analysis of variance. So length is a function of dose, data tooth growth, and we get a summary. Now, because we're doing multiple comparisons, I'm going to use this EM means, estimated marginal means, also known as least squared means, for this outcome by dose, and then I can get contrast and adjust with a post hoc test of Tukey to really tell, like, okay, if there's a significant difference in the model, where are the differences? Where are the differences between groups? It's pretty straightforward. With Bayes, the setup is ANOVA Bayes factor, same sort of setup. Length is a function of dose. We can do our posterior change, and also did quite a bit of other things to try to pull out some of the information, because now we're looking at multiple groups. Try to pull out some of the information to put in a different data set to actually graph multiple things at once. So I didn't show all the code here. If you want to see all the code here at the end of the references, there's going to be a link to a GitHub page which has all the code that I ran. So anyways, I can do a plot to hopefully show things all at once. Anyway, so this is what the data sort of summarized looks like. You have different doses, and it really looks like, yeah, that as you increase dose, the length of the tooth or the tooth cells increases. So if we run our one-way ANOVA, for the overall model now of the effective dose, we see that we have a significant p-value. Now, because it's significant, we can do a post hoc test to see what is significant. So that's why I did those least squared means. You can contrast here, and it looks like every comparison against every other comparison is significant. For Bayes analysis, we can have our Bayes factor. Now, again, because there's scientific, sometimes it expresses in scientific notation. There we go, scientific notation. So it's not just 4.98, it's 4.98 times e to the 12. So this is like, was it millions, billions? Anyways, so make sure you're keeping track of whether or not it's scientific notation or not. So this is extreme evidence for the alternative hypothesis that there's no difference between any groups. And so what I did with my additional code for a GG plot, I was actually trying to plot sort of the estimated means, or at least estimated difference between means of all three groups. You can see that this really tracks here. The highest is the high dose, the lowest is the low, the medium is the medium, and there seems to be the high and the medium seem to be closer, just kind of what we saw with that box plot. So we'll now go to 2A ANOVA. We'll use tooth growth again, but now we can add additional variable. We're going to use dose, and we're going to actually also add the supplement, and then we'll actually can also look at the interaction. So I'm going to add the interaction term. Now you could also just do dose times supplement, and that would give the individual terms and the interaction, but I like to just write this all out just to kind of show what we're trying to do here right now. All right, and you can summarize it. Again, do estimated marginal means and contrast everything. Do the same thing here for Bayes. Now, because we're starting to get more potential models that we can look at, we can start just, because by default Bayes factor, we'll calculate all the models. So we'll calculate the model for length and dose, or length as a function of dose by itself, dose and supplement, supplement by itself, et cetera, et cetera. Now, I mean, there's not a lot of models here comparatively, but there are enough, especially when we build out more and more variables, that there could be an impractical amount of models to look at. So you want to just look at like the top models. So you can do things like that, where you can have setups where you can say, just give me the top models, or etc. And then as you're doing summarizing and plotting, you're going to need to subset what specific chains or plots or anything that you want to specifically look at. I mean, you can by default look at everything, but that can kind of get unwieldy. Anyways, so this is sort of the underlying summary of the data that we're looking at here. Again, we've seen that things seem to increase by dose. The supplement is now the color. You can see that at least on the lower ends, the VC that's the ascorbic acid, as opposed to the orange juice, seems to be lower, but sort of disappears at the high. So there might be both a dose of supplement and an interaction, that one they change at different rates. So with the traditional, we found that in our model, again, are the different variables in the model. We see that they were all significant, and if we do estimated marginal means, there's a lot of comparisons because there's a lot going on here. And so really I just highlighted all the ones that are significant. There's only 4 which weren't significant, which is actually helpful to start looking at a graph now of the arrows of the ones that weren't significant. So unsurprisingly, this OJ here in low was not different from VC here, and then the medium OJ was not different between any of the high ones, and then the 2 high were not difference between our supplement. So that, but everything else was significant. For Bayes, again, this will pull out the different models. So 1 is just supplement only, 2 is dose only, etc., and it gives various things. You can see here that model 4, index 4, the full model is actually the best fit model, as the highest Bayes factor. You can say, okay, this explains the data the best. Now, once we start going to ANOVA and regression, where there will be a lot of variables, we can compare a lot of models. My sort of frequentist sensibilities gets a little squirrely, because especially when it comes to sort of like the standard regression, you add only variables that you think are relevant, and you run them, and doing like forward and reverse selection is popular in some circles. Like I find that, and I'm sort of convinced that that's the wrong way to do things, and it's improper. So I sometimes have a quibble with like, okay, if you run the model and you're doing all this model comparisons, is that appropriate or not? Anyways, that's a greater, I guess, maybe metaphysical argument. Maybe we'll stick to just how to run Bayes factor, and you can decide from there how you want to do model selection or model selection at all. But anyways, with that, NX4 had the best model, again, scientific notation here. So it had extreme evidence for alternative that at least there were some differences. And now, so this was just the full thing. If you wanted to, you can do things like top-down analysis where you can omit different variables to see how that changes. And if you try to omit anything, these are all less than 1. So this scientific notations with this e to the negative 16. So if you submit anything, it actually reduces model fit because the factors are less than 1. So there's a lot of things you can do with comparing models in Bayes factor when you get into ANOVA and regression with multiple variables. So saying the same thing is the models, especially including all the terms and the interactions, were the best model and significant. All right, repeated measures of ANOVAs. I'll use the data set puzzles. These are puzzle completion times across a couple characteristics. So we're going to use shape and color. And here, so R is, I think, response time, and shape multiplied by color means shape, color, and then the interaction term. And now because it's repeated measures, so I think, yeah, different individuals tried these times with like different shapes and different colors. So there's this ID term that links the individuals. So that's the repeated measure. One individual did multiple treatments. And so we can do this error term with the ID / shape times color, so we can account for that repeated measure, sort of like the paired relationship in the paired t-test. And we can do a post hoc test from there. With Bayes, we can a little bit different setup with here, where the formula is y as a function of one of our x variables plus ID, and then we do need to set this other option, which random. So what's the random effect? Because essentially that's what repeated measures is sort of a random effect. You can set it as ID. You can plot things, and because how Bayes factor by default, like the null model, is set up, you can actually set up what null model you want to do. So you can do things like create a model without the random effects, without that ID term. So BF without ID, you can have that here. You can have only ID, so just as the y is a function of our repeated measure of the ID. You can have these things here, and you compare your ANOVA, your different models to those things to sort of compare. Did repeated measures matter? Did including for ID matter? So, and then summary of what we're actually looking at with puzzles here. So response time on the y. See here that there's 2 variables for shape, round or square, and then 2 variables for color. So color or monochromatic. Looks like monochromatic had a little bit higher completion time. Difference between round and square doesn't really look that much at all. So we can run traditional, and just how this sets up with it's a little bit different here because we have repeated measures, but we can see here shape looked to be significant, color looked to be significant, but the interaction term did not appear to be significant. We do some post hoc tests, and really all we see that was different between the different contrasts was the square color versus a round monochromatic. So it looks like, yeah, this response time was higher than this response time, but that was the only one that was actually different. Now with Bayes factor analysis, again, we can have the different models. Looks like the stronger support, there's a strong evidence for alternative model with shape, color, and ID, but not the interaction term, which we saw in the traditional. And this was comparing against just the nothing but the ID, the random effects. And you actually plot things like this in Bayes factor. You can look at the difference between models here. I find that just these tables here do the same sort of thing, and they're a little bit less flashy. It's your choice here. But looking at our additional models where we ran them Bayes factor specifically without ID or only ID or with versus without, you can set up these different things against, say, intercepts. And the real point here is when we did the ones with ID versus without ID, it was very large. The Bayes factor is very large. So our alternative hypothesis that a model with ID was a printer or null of without ID, it was very high. So adding random effects was much preferred. So models with random effects or repeated measures compared to just a standard ANOVA were preferred. All right, we're done with ANOVA. We're on to correlation and regression. So we'll cover, unsurprisingly, correlation. Then in the regression front, we'll do simple linear regression, multiple linear regression, logistic regression, and Poisson regression. So with correlation, we'll look at the famous iris data set, either Fisher's or Anderson's, measurement of sepal lengths, petal lengths, and widths for flowers, 3 species of iris. So we'll use a correlation test for the traditional. So y is going to be a sepal length and x equals sepal width. Again, the difference between correlation and regression is correlation is sort of undirected. You're just looking at, is there a correlation between the y and the x variable, whereas regression is more directed, where, is y predicted by x? So, what y and y x is matters, where in correlation it really doesn't matter. It's just like a comparison. There's no directionality. Anyways, so Bayesian, we can do correlation BF, Bayes factor, same sort of setup. We have a y, we have an x. We're doing sepal length and width. We can do same sort of chains, plots, etc. with the Bayes setup. And this is what we're working with here, sepal width on the y, sepal length on the x. You can see here that there's really doesn't look like there's any correlation. Probably there looks to be some additional patterning. I suspect if you actually added in information like species, you'd see stuff here. But again, we're just sort of doing this very simply. Broadly speaking, between sepal length and lift, there looks to be no real correlation. But the test here is going to tell us that. And yes, in fact, we saw a p-value of 0.15, so it's above 0.05, so it was not significant. And the correlation was fairly low it was slightly negative, so as one increased, the other decreased. Slightly negative at 0.117 or 112 or 12. With Bayes factors here, we got our first fraction is 0.5. So there's anecdotal evidence for the alternative hypothesis, or sorry, the null hypothesis. That is to say, there's some evidence, anecdotal evidence, that there's no real correlation. We can do a plot here. In fact, now when we're getting to regression and trying to get things like correlation coefficients out, it's helpful to actually plot some of the outputting data tables. You can get various things like means and standard deviations for variables. And so we actually want, for our correlation, our row, we can get our mean out. You can see here that it's 1.11, so very similar to 1.1 or rounded up to here. And then if we plot this, see the correlation, yeah, it's negative, but really, yeah, falls, 0 falls plausibly within that distribution. So there we go. All right, simple linear regression will be pretty straightforward, but now we're directed. Now we're using the dataset attitude. It's from a survey of clerical employees of a large financial organization. And there's a variety of variables, but I only use one of them because it's simple, which means it's one y variable, one x variable. And so I'm going to use the function LM, linear model. So our y variable we're trying to predict from our x variables is rating. Can rating be predicted from the variable raises? In this data set, and we'll summarize it. Bayesian, we've already set up two regression BF, Bayes factor, rating as a function of raises. You can sample from posterior and get a summary. So this is just a quick data graph. We see here, yeah, that looks like as raises increase, so does the rating. So we would sort of suspect. We run a traditional analysis. Again, now we're getting to regression, especially getting just a point here. When you're running a good statistical analysis, you should be testing your assumptions and doing model fit and all that stuff here. I'm not trying to indicate that you should do that, but I'm skipping over that sort of thing and just running the very simple tests, making the assumption that those are valid. When you actually do this, you should do that first, but that'd be getting more into the weeds. So just a point of order here. Anyways, we see that raises was significant in our traditional model here, less than 0.05, and then we have an estimate for that, the actual relationship, 0.69. So that would be essentially the slope of our line. And we can get things here if you care about r squared, etc. And in the Bayes side of things, 47. That's the Bayes factor. That's very strong evidence for the alternative, so that there is a relationship between the two. And again, you want to probably pull out actual means and standard deviations from variables. And we're looking at raises, and we see here this is estimated slightly different, about 0.61 compared to 0.69. So a little bit different. Obviously, there's different things under the hoods here, but they're pointing in the same direction. All right, multiple linear regression. Now we're going to add more x variables. Use the same attitude data set, but with our linear model, we'll include complaints, privileges, learning, critical, and advance, along with our raises. Now, of course, we could have variables interaction terms, but for this, especially because these are all numerical, I would advise against it. Interaction terms make more sense with categories, but anyways, there's a lot you could do, and you could have done less, but here's just throwing everything at the wall here. And with Bayes, same sort of thing. Looks very simpler. Now, because there's a lot of variables, there can be a whole lot of models, so you can sort of cut down on how many you actually want to show by either doing like Bayes reg. That's the Bayes reg 2 is our object with all this information. You could just subset by like just the one model, like the full model you want, or you could do something like the head and just it'll show you the first 10. Because starting to interpret what Bayes is spitting out becomes important with the more variables you add. I just did a correlation of all the variables here. The important thing here is we're looking at rating, so maybe just this first column here. Obviously, the diagonal you ignore, but it looks like complaints seems to be strongly correlated, to a lesser effect, learning and raises. Privilege is a little bit less here, and critical and advanced seem to be the least correlated with our y variable, our rating. So we're going to run this out here. The model here is going to look at all the different variables, and it looks like we're including the full model, so only complaints was significant. So it looks like raises, when considering all the other variables, was no longer significant, though we did see that in our simple model. That's one of the tricky art form like approaches that you need to do with multiple linear regression. There's all sorts of ways you can build your models. And so you need to really think hard about how you put it out there. There's no one exact way of building your models. You have to, think through it, and sometimes a dance of art and science. Anyways, then there's the F statistic, which is going to come into play here. This really tells us whether the overall model is significant, because sometimes the t-values and p-values here are for specific variables. Sometimes we want to just care about, we usually want to look at the overall model, is that significant, and then only look at the p-values and t-values if the overall model. And the overall model is significant. So we go here and it looks like complaints are fairly significant. It's a positive. So apparently the greater the number of complaints, the greater the number of raises. So there's that. And for Bayes, just an important point here, there are 63 models of all the different combinations of variables and combinations of variables. So it's a lot to look at all of them. So if you just look at the full model, there seemed to be extreme evidence for the alternative hypothesis. But if we looked at sort of the first 10, and I believe these are the top 10 models, we can see here that the model with just complaints had the highest Bayes factor, suggesting that maybe just having a model with complaints predicted raises the best and nothing else. And then I pulled out here, just to save space, looking at the complaints, the estimate, the mean, sort of we can see here that the means were broadly similar. We're doing traditional and Bayesian, and standard deviation was fairly similar, but notice that Bayes had a little wider standard deviation. All right, we're on to logistic regression, which is essentially regression, but the y variable is binary, so it's 0 or 1. And so we're going to use span base. So I'm calling this span base 2. Span base is a 1, or just the regular span base is well-known data set with binary target that tries to predict whether something's spam or not. So 0 is not spam, 1 is spam. There's 48 attributes. It's a huge data set with the different attributes of like the frequency it appears in the email. I made spam 2 with this is spam variable a factor, and then I just subset because it's so huge. So really there would be significance everywhere because you have such a huge data set. So I just sampled 500 just to have something to work with here that maybe we'll show things that are significant and not significant. So traditional approach, I'm going to need to use the GLM, so generalized linear model. And so our y variable is spam, so it's going to be a binary variable. I'm going to have I selected some of the attributes I thought would be the most relevant. So word frequency of money, free, credit, font, education, and 1999. And because this is a generalized linear model, I need to specify the family as binomial. So for that logistic regression, the binary data, 0, 1. Otherwise, it would just be a multiple linear regression, and that would get really messed up because you don't actually have a continuous numerical variable for your normal regression. Anyways, and I can summarize this. Bayesian, very similar. You can use Bayes reg, and you will do instead of family, it's model. You need to say model as logistic. So with traditional here, we saw that the free, credit, education, and 1999 were significant. Free and credit, these were positive, so they significantly positively predicted whether it's spam or not, where education and 1999 negatively predicted. So the more likely there is edu in an email, the less likely it was actually spam, which would make sense. But the more likely it said credit in there, the more likely it was spam. And Bayesian, so the way this one runs is a little bit different here. We'll see some of these things. This is where it sort of spits out this Bayesian parallelized regression estimation. Gives some of the parameters that it runs with, but then really what we're getting here is the different parameters and the rank, and you get something that's analogous to a t-statistic, and then the ranking is how the lower is how strong it is. So for example, if we look over at the traditional here, education, it had an estimate of negative 2.4. The t-stat over here is 2.8, so similar. And this is like rank 1. Same with 1999, rank 1. So these are like these two are the strongest sort of predictors, the strongest rankers in this. Whereas something like frequency or free and credit are in the middle, and then the ones that we find that weren't significant, like money and font, were lower rank. So a little bit different setup here. All right, finalize some regression. Poisson regression. Poisson typically like count data, so 0, 1, 2, 3, as opposed to sort of numerical continuous where they can be decimal. That'd be traditional regression. We're using the warp breaks data set. It gives a number of work breaks per loom, where loom corresponds to a fixed length of yarn. So we're going to use two variables, wool and tension. Both are actually categorical because it turns out in linear regression, your y variables should usually be, depending on what type of regression is dictated, but the x variables can be categorical or numerical, etc. So these are numerical. We'll need to set the family of Poisson. And for Bayes, against Bayes reg, we'll need to use the model Poisson. You can actually turns out, you can modify your burden. That's using some of the characters of the MCMC. I think by default it's probably 10,000, but you can specify it if you want more or less for your requirements. All right, and just to sort of clarify what we're kind of looking at here, looking at the different wool types by themselves, A and B, looks like wool may be about the same. A may be a little higher, but a lot bigger spread, whereas tension really looks like there's higher breaks at low tension, intermediate at medium, and then the lowest at high. But where the real difference is here, and we can combine them together here. It looks like wool A at low tension has the highest breaks, but a lot of variability there. So we run this Poisson regression here. We see that wool, tension, and some interactions were significant here. You have to, because we have multiple variables and multiple categories, you have to start really trying to parse out things here, but those look all significant. If we run the Bayesian, again, so wool B this is a little confusing because it's not just wool B, it's wool B compared to the default, which is wool A, or the reference wool A, which is tension M, isn't just tension M, it's tension M versus high, which is going to be the reference point. And you can change the reference categories, but I didn't. And then tension high versus, or sorry, not medium, medium versus low, and then high versus low. And so medium and high were higher than low. If you wanted to compare medium and high, you'd have to switch things up and make things more complicated. So we're not going to do that here for now. And then again, with these combinations here, it's wool B and tension M versus the default. And we can see the same variables here and same, but again, we're getting to things like ranking where tension had a much greater effect on the model, higher ranking than something like the wool type or interaction terms, which sort of makes sense. We really did delineate, okay, it looks like low tension had the highest breaks, and as you ratcheted up the tension, it decreased warp breaks. All right, that's that with regression. We'll turn to frequency analysis. Some of these will be just two here. proportion test and chi-square test of independence. Relatively straightforward here. We'll start with a proportion test. We're going to use, well, we don't even need a data set. We're just going to do, I'm going to create what's called coin flips. Imagine, because you're looking at proportions, we want to look at proportions of something like heads. And so imagine you flip the coin 100 times and you get 63 heads. Is that significantly different than a proportion you're interested in? Now, with a proportion test, obviously, sort of like a t-test, you could have a sort of like a one-way proportion test, maybe you would call it, where like you're comparing against a constant. So in this case, we're looking at, it's the proportion of our test, so 63 heads out of 100, so 0.63. Is that different from sort of totally even, so like 50% chance, 0.5, or like 50 heads out of 100? You could also do almost like a two-way proportion test where you could say, well, Susie is going to flip the coin 100 times and Joe's going to flip 100 times, and they're going to compare it. Are their head flipping, the proportions different between the two? So we're just going to do the proportion test as is. Again, you can expand it to multiple one or two-way proportions. So we're going to use the function binom.test. So our x variable is 63. The number total is 100. And the proportion we're looking to compare against is 0.5. We can do proportion BF, Bayes factor, same sort of setup here, and we can test posterior, etc. And so what we find here with the exact binomial test for 63 heads out of 100 compared to 0.5 as our proportion, the p-value was significant because our probability of success was 0.63 compared to 0.5, and that was significant. If we look Bayes, our factor here is going to be 5.9. It has moderate evidence of the alternative, so that it really is a moderate evidence that 0.63 probability is different than 0.5 probability. So still pointing in the same direction, but Bayes maybe is a little bit less certain about whether it's actually different. And you can plot things here. This is like the density here. You can see here that, yeah, well, the most likely outcome, the true proportion, yeah, is in the 60s, but doesn't totally preclude 0.05. There's still some chance that this could happen under the null. All right, next we're going to go to the chi-square test of independence. We're going to start out with the survey data set, but then I'm going to, what I'm calling S-hand data frame. So it's going to look at essentially handedness by sex. So these are frequency data, these are counts. So we're going to see if there's a difference between sex, male and female, and handedness, left or right handedness. And so with the traditional approach, you need to sort of get things set up here. First, I'm going to just parse out the difference between left and right-handedness between sex, just so we can see what tables we're going on here, and then you can do a chi-square test against the data frame. The Bayesian approach, you can use what's called contingency table, BF, Bayes factor. You're going to need to put in your data set, your sample type, how your fixed margin is a little more complicated, so certainly walk through some of the references I have for this to get a better understanding. And you can this frequency, you can do plots, and then you can specifically look at things like creating objects like what's the probability or the probability of left given male, left given female, to really piece these out a little more, and you really have to dig into the specific pieces of this chain object, and then you can plot actually the MCMC of these. It'll make more sense actually visualizing it. But really, what we're looking at here, this is the frequency data here. We're looking at the counts. So this is number of left-handed. There's a total of 17, 7 female, 10 male. And there's over 200 right-handed, so obviously left-handed is in the minority, right-handed, and there's 110 female, 108 male. And the question is there a difference between, handedness by sex? Do males tend to have higher, lower, left or right-handedness compared to females? And so traditional, if we do those simple calculations, it turns out the percentage of left-handed females was 6.4%, where the percentage of left-handed males is 9.3%. So there's a high percentage of males who are left-handed compared to females. But is that significant? Well, if you do a chi-square test, you find the p-value is resoundingly no. There is no difference. And if we run Bayes, it's a fraction, so there's moderate evidence for the null hypothesis that there is no real difference in handedness between males and females. There we go. Oh, right, that plot I was telling you about, the MC left given male, left given female, you can get this data here. And you can kind of see here what it's showing is, I think right here would be 0. It really falls, this density, the comparison between male and female really falls in with a 0. So there's really no evidence, no confidence that it's these differences are actually significant. Really, handedness looks to be independent of sex. That's really the test of independence comes from that. It's independent of sex. If this was significant, these variables were significant, or there's evidence for the null or evidence for the alternative, that means there seems to be dependence that males were more likely or less likely to be left-handed or something. All right, we'll close out here with some advanced models here. I'll be looking at what I consider my bread and butter, the generalized linear mixed model, as well as looking a little more into survival analysis, which kind of looks at things differently and is very common in the medical fields. So a generalized linear mixed model, which is really, we've been building up towards that with a lot of regression. A generalized linear mixed model, the generalized means you can have different distributions. So again, we always saw things like logistic and Poisson. You can do things like that, or even things like negative binomial, gamma, whatever distribution. The linear, so again, x and y variables, that can be categorical and numerical. And the mixed is, again, adding in random effects. We sort of saw that with ANOVA, where the idea was a random effect. So you can, these are the most flexible models. You can do a lot with them. And so we're going to use the data set cake, which is data on the breakage angle of chocolate cakes made from different recipes, different temperatures. It's a split plot design. So there's some replication. And so we can kind of dig into all that. So I'm actually going to do quite a lot to sort of build up our models here, just to sort of figure out things as we go. So I'm going to have a summary of 4 models, and we're going to start with just a linear model, so no fancy generalized, no fancy mixed. We're going to say angle, that's going to be our y variable. We're trying to predict angle. We're going to see, well, can angle be predicted by recipe and temperature? So that's just a basic multiple linear model. But then we can say, well, what if we add a mixed effect, a random effect? Because we have replicate information. So we can add that as plus 1. And these need to be in parentheses 1 and then slash replicate. So they'll show that is our random effects. And we could use limmer. And we can use glimmer, which is going to let us use a generalized distribution, so we can try Poisson. Now, unfortunately, in R, glimmer does not let you use negative binomial. You need to use a specific function called glimmer NB, negative binomial, so you can do that as well. And we can test that one and see which has the best model fit. Bayesian approach, we're just going to go to general test Bayes factor, and we're going to use which random as replicate, and I don't think we're in this one we're having a different distribution, and we can do various comparisons, including you'll kind of see where these come into at the end here. All right, just kind of where our data is. This is the angle data here, and you can see it's probably not normally distributed. It's more like it might be better conceptualized as something like a negative binomial. That's why I did it here. And if we look at the recipe, it doesn't look like there's much difference between recipe, but it looks like there might be some difference between temperatures. So this intermediate one second to highest, I think, is 275. Might be the highest. So if we run traditional here, and I'm going to start with our linear model. It looks like the only one that was really different is temperature, what they call L. Yeah, it was really weird. Their variable names for some reason really popped up weirdly, but essentially this is I think the lowest temperature compared to the highest temperature. I think the highest temperature is the default comparison. And we saw the same thing if we add a linear mixed model, so add a random effects. By the default, that modeling doesn't actually give you p-values, but you can infer with this t-value that, yeah, that's actually helped the model, higher t-value. If you looks at like a Poisson model, remains significant, and if you use a negative binomial, it is also very, very similar here. The difference between seeing maybe which models you would actually use will go into something like model fit, which is sort of beyond what we're trying to do here. But in any case, looks like this is the lowest model was, or the lowest temperature was significant was from the highest temperature. Now, you could set up things in different ways. You can actually compare like different temperatures between each other, because it really looks like this one's the highest one, and so you might want to actually, because really this is all, I think, the models are compared. I guess no, maybe this is maybe highest. Anyways, you're only comparing each of the temperatures to a reference. So I think what this must mean is temperature L must be here compared to this one, because that's positive, so it's higher, whereas everything else is not. Does that? Well, let's turn to Bayesian. I think this will shed some light, hopefully. So if we look at the fit factor analysis, look at the models, looks like there's the best model is temperature and replicate, and there's extreme evidence for that alternative hypothesis. Now, what I'm trying to show here with sort of this data spitting out of the mean is temperature at 175 is here, and temperature 225 is here. So there's a difference of about 6. So yeah, whatever this is a difference between the lowest and highest temperature. But you can, and then you can plot things like that. And so there's, again, a difference of about 6 between negative, well, more like 7 between negative 3.9 and 3.0. But you can, thinking back on there before we go to survivor analysis, you can do additional comparisons. That's why I had in some of the code, but I didn't show it. You can like compare different temperatures, and you can see that second highest temperature was significantly different also from the lowest temperature, but it wasn't significantly different, or wasn't, there wasn't evidence that it was different from the highest temperature. Anyways, so complicated stuff. Yeah, as you get more variables, things get more complicated, and you have to be very careful about what you're being comparing and modifying data. With all that in mind, let's get to the tricky thing called survival analysis. So we use the data set Veteran. It's a randomized trial of 2 treatment regimes of lung cancer, a very standard survival analysis data set. So traditional approach, we're going to need to create a sort of survival object. So we're going to use the function capital serve. So we're going to need to time. So again, see, this is time to event data. So time M, and the veteran status. Status is essentially whether they're, this is the survival outcome. Survival analysis doesn't mean necessarily need to be death, but it typically is death, or dead or not dead. But it can also be time to event, like time to incidence of cancer, time to divorce, whatever, but the most standard is time to death. So you're either dead or alive after a certain amount of time. And survival analysis often has censoring, because not everyone dies, in the time frame that you're looking at, or not everyone gets the thing, so that data is censored. You know that they survived to that much time, but you're not sure how much longer. So then a couple different models I'm going to do here. First of all, I'm going to fit one model called using SurvFit. I'm going to take this survival object. I'm just going to do 1. And what this is going to do is just look at just overall, this is going to be survival plots, survival curves. So it's just going to do the overall survival. But then what I can do here with the second one is actually from Data Veteran, I can get this treatment. So if you look at, because really what we're trying to answer here with most survival analysis isn't what's the pattern of survival is, well, did one survive compared to a treatment or an observation or some sort of characteristic? Maybe you do it by sex, maybe you do it by race, or if you're doing a study, you probably do it by some sort of treatment, some sort of intervention. So in this case, it's treatment. There's 2 different lung cancer treatments. So we're going to check that out, those graphs out. And then actual survival analysis, we can do a Cox proportional hazards model. So we have our survival object here as a function of treatment, and we can do some various summaries and then also plotting them. For Bayes, there's Bayes Serve was the best one I could find here, and really, unfortunately, you could plot a lot of survival plots just by themselves. I really wasn't able to find good tests for the actual treatment, but you'll kind of see, you can at least plot things. You can't really get test statistics out, but you can certainly plot things. So this is kind of what the very raw plots look like. This is survival over time. You can see as it drops. I think this is a data set which fairly complete, where you get a long period of time. By then, essentially everyone is dead. And you can look at the different treatments. So there's a standard and the test. You can see that the different colorings. There doesn't seem to be us evidence that the 2 treatments are different in survival time. But you can actually test that. So our Cox proportional hazards model. So we total of 137 patients, 128 had the events. The rest were censored. The p-value was 0.92, so not significant. And then the odds ratio, which is like right here, kind of shows the difference between the 2 tests, but there really wasn't a difference. It was almost 1. So there's really no difference between the survival between the 2 tests. For Bayes, because unfortunately they really didn't spit out these sort of Bayes factors or anything analogous to the actual Cox proportional hazards, like odds ratios or p-values or z-values. It would pull out tests, so you could do the different credible band, or you could do Kaplan-Meier curves, you could do hazard curves, things like that. And if you pulled out the right data here, you could actually get curves from the posterior of the different treatments. So I wasn't that happy with a quick and easy way to do survival analysis and Bayesian analysis. Not that there isn't, it just there's an easy way for easy comparison against the standard in R. All right, well, that comes to the end of our time here with doing things, but there's certainly more things you can do if you really want to dig into Bayes. And you can find some of the references. Obviously, maybe you want to start doing structural equation models or generalized estimating equations or generalized additive models or even non-parametric models. Those are all trickier, certainly trickier in the frequencies method and also trickier in Bayes, but that doesn't mean you can't get them done. So references here, hopefully this was just an introduction for you. Here's a bunch of references, and they should be in the link in this video here as well, the description. I would say if you want all the code of what I ran to run it yourself, you go to my GitHub. This is statistical models resources, and then it's the Bayesian methods. It's an RMD file. And there's more references for the different things I run, including Bayes factor, that was the biggest one, as well as other stuff with Bayesian regression, including some more advanced resources if you want to go above and beyond. So to close, thanks for joining me. This is funded by TRANSCEND. So if you found this useful, you can cite this. You can cite TRANSCEND as a resource you used. All right, go forth and use statistics wisely.